Hello friends, today I will discuss the parallel resonance. In this topic, I will cover definition of the resonance, variation of the impedance with frequency, variation of the impedance at frequency resonance, similarly impedance at half cutoff power frequencies, and current at resonance, bandwidth, lower cutoff frequency, upper cutoff frequency, and power factor variation, and also the variation of the voltage across the circuit with respect to the frequency. So what is the definition of resonance? The resonance is nothing but when voltage is applied, AC voltage is applied, the AC circuit, if the applied voltage and the current are in phase, then the circuit is said to be in resonance. So let us take a circuit here. This is the resistance, this is the inductance and capacitance. All are considered as pure elements. So and they are connected in parallel across the AC supply whose frequency is variable. Here the impedance of the capacitance is represented as Zc, which is equal to the minus Jxc. Similarly, the impedance of the inductance is represented as Zl, that is equal to J into XL. Similarly, the impedance of resistance means it is Zr is equal to R. Because it is a parallel circuit, it is easy to analyze with the admittance. So the admittance of resistance is represented as YR is equal to 1 by ZR. Similarly, the admittance of inductance is represented as YL is equal to 1 by ZL. Similarly, the admittance of capacitance is represented as 1 by Zc. So for this parallel circuit, it can be written as Y is equal to, that is total admittance of the circuit is equal to YR plus YL plus YC. Having known YR, YL, YC, substitute here. So that is Y is equal to 1 by R plus 1 by JXL minus 1 by JXC. So after further simplification, we get 1 by R plus 1 by JXL minus multiply numerator and denominator here with J like this, and this denominator J into J becomes J square, so that will become, its value become minus 1, and here is another minus 1, minus this minus 1 and this minus multiplied, so that similarly here we have the 1 by JXL, multiply numerator and denominator with J, so that this will become J square, so that is minus 1, and here this will become minus J by XL like this, and when it comes to this minus 1 by JXC, when it is multiplied its numerator and denominator with J, and this denominator J into J becomes J square, that J square is nothing but minus 1, and here is minus 1, so minus 1 into minus 1 means it will become plus, so it will become ultimately plus 1 by XC into J. So after rewriting the equation, we get Y is equal to 1 by R plus J into 1 by XC. Because it is plus, it will become plus, so first it counts 1 by XC. Here this will become minus, so minus 1 by XL. At resonance, the imaginary part of the admittance is 0. So this J term will become 0. So that is 1 by XC minus 1 by XL is equal to 0. From this, it can be written as xc is equal to xl. So xc is nothing but 1 by omega r c, and xl is omega r into L. Here omega r is the angular resonance frequency of the circuit. After simplification, it becomes omega r square is equal to 1 by LC. So from this, omega r can be written as omega r is equal to 1 by root LC. And coming to the variation of the impedance with respect to the frequency, it can be observed like this. So here, in the initial stage, the inductive reactance is more than capacitive reactance up to resonance frequency. After resonance frequency, capacitive reactance is more than inductive reactance. So in this region, power factor is lagging, whereas in this region, power factor is leading. And here, coming to the impedance, so at the lower frequency, means less than resonance frequency, the impedance is low, so gradually increases. At the resonance frequency, the impedance reaches its maximum value like this. Then after resonance frequency, the impedance starts reducing like this. So here at maximum impedance, resonance is occurring, and the current that flows in the circuit will become minimum due to the higher impedance at resonance frequency. Whereas in other regions, the current is higher. So this circuit, this parallel circuit is called the resistor circuit, and the power factor at resonance frequency is unity, and the current here is a minimum. Here, the voltage at resonance in this circuit is maximum like this. So this shows the voltage variation with frequency with respect to the frequency less than resonance frequency. The value of the voltage across the circuit is lesser. Once it reaches the resonance frequency, the voltage across the circuit is maximum, and after resonance frequency again the voltage starts dropping. As discussed earlier, this is the current curve, which is minimum at the resonance frequency due to the higher impedance at the resonance condition. Here, to get the half power cutoff frequencies, we divide V max divided by with root 2. This is the maximum voltage condition, whereas here this is the half power frequency voltage, that is Vm by root 2. And in this condition there are two frequencies on x-axis. One is f1, that is lower cutoff frequency, f2 is upper cutoff frequency. In these two conditions, the voltage across the circuit is same and the impedance also same. Next, having known the resonance frequency, that is equal to omega r is equal to 1 by root LC, so which can also be written as Fr is equal to 1 by 2 pi root LC, bandwidth can be calculated. So let us see what is bandwidth derivation for this parallel circuit. At half power frequencies F1, F2, the admittance of the circuit is same, that is YF1 is equal to YF2. As known from the fundamentals, current is directly proportional to the admittance. So it can be written as like this: 1 by Xc minus 1 by XL is equal to minus 1 by R. So Xc can be written as 1 by omega 1c. At lower cutoff frequency F1, XL is dominating or XL is more than XC. So if when we write omega 1c minus 1 by omega 1L, that will become equal to minus 1 by R. So after further simplification, the equation will become like this: omega 1 square LC minus 1 is equal to minus 1 by R omega 1 into L. After further simplification, equation becomes omega 1 square LC plus 1 by R omega 1 L minus 1 is equal to 0. So it can be further simplified as omega 1 square plus 1 by RC into omega 1 minus 1 by LC is equal to 0. So from this it can be written as omega 1 is equal to minus 1 by 2 RC plus or minus the root of 1 by 2 RC whole square plus 1 by LC. Similarly, at a higher cutoff frequency F2, XC is more than XL. So omega 2C minus 1 by omega 2L is equal to 1 by R. From this, omega 2 can be written as omega 2 is equal to 1 by 2 RC plus root of 1 by 2 RC whole square plus 1 by LC. As it can be seen from the graph, bandwidth is nothing but omega 2 minus omega 1 or F2 minus F1. By substituting the value of omega 2 and omega 1 here, then it becomes as 1 by 2 RC plus 1 by 2 RC, which is equal to 1 by RC. For all practical purpose, 1 by 2 RC whole square is much less than 1 by LC, so that 1 by 2 RC whole square can be neglected. With this assumption, omega 1 and omega 2 will become omega 1 is equal to minus 1 by 2 RC plus root of 1 by LC, and this 1 by root LC is nothing but omega R. So this omega 1 equation can be rewritten as omega 1 is equal to omega R minus 1 by 2 RC. Similarly, omega 2 can be written as omega 2 is equal to omega R plus 1 by 2 RC. Then bandwidth can be written as omega 2 minus 1. So bandwidth BW is equal to omega 2 minus omega 1. So once their values are substituted and simplified, that will become 1 by RC. And omega is known as is equal to 1 by 2 pi f. So resonance frequency can be written as 1 by 2 pi root LC. Substituting this value in the lower cutoff frequency and higher cutoff frequencies, then F1 will become F1 is equal to FR minus 1 by 4 pi RC, and F2 becomes F2 is equal to FR plus 1 by 4 pi RC. So again, bandwidth can be written as F2 minus F1 is equal to 1 by 2 pi RC. Let me summarize once. Here parallel resonance frequency was obtained by keeping the pure elements resistor R, L and C in parallel with the variable frequency AC supply, and it is observed that resonance is nothing but the voltage is in phase with the current, then circuit is said to be resonance, and it is also observed that the variation of the impedance with respect to the frequency, and it is maximum at resonance frequency, and it is observed that resonance frequency occurs at maximum impedance, that is current flowing at resonance is minimum, whereas the voltage across the circuit is maximum at resonance frequency, and it is also observed that the impedance at half power frequencies is the same, and also obtained resonance frequency as 1 by 2 pi root LC, and also obtained bandwidth, and also obtained the relation between the resonance frequency and the lower cutoff frequency, and also resonance frequency relation with the upper cutoff frequency, and also observed the power factor variation, so which simply follows the voltage curve in the circuit, and it is maximum at resonance condition, and also it is observed that XL is more than XC below the resonance frequency, whereas above the resonance frequency XC is more than XL, so the power factor is lagging below the resonance frequency, whereas the power factor is leading above the resonance frequency, and power factor is unity at resonance condition.